Okay, hello everyone, and welcome to part two to the introduction on exponentials and logs. In part one, we did a review of exponentials, what characterizes an exponential, what is exponential growth, and how to graph exponentials. We also had a sort of introduction to what's called Euler's number being E, which is 2.718. Or roughly, that's an approximation. I already talked enough about that number in that video, so we're going to pick up right from there and continue the lesson. Getting towards what we want to talk about in this video is logarithms. Okay, so the next thing we were going to discuss is to take a look at an exponential function and look at its inverse. So in the previous video, we made a table for f of x as 2 to the x. So if this was x and this was f of x, on the previous page, we plugged in some numbers. 0 gets you 1, 2 to the power of 1 is 2, 2 squared is 4, 2 cubed is 8, okay? And so that's the function in question that we're referring to, okay? What we're going to do right now is take a look at what would the inverse happen to look like, right? If you were to take this table and just swap the x and y values, that would show the inverse graph. And you've never really talked about inverse exponentials because inverses were introduced this year in Algebra 2. So all I really have to do is take this table of ours and swap x and y, right? 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. 2, 4 is now 4, 2. 3, 8 is now 8, 3. And so we'll just plot those points, right? 1, 0 is right here. Then 2, 1. Then 4, 2. And then 8, 3. Like so right there, okay? And so that's the graph. Except, okay, maybe there's a little bit more work that I need to do here. We also found some fractions. When we plugged in a negative exponent, we got a half. And then when we did -2, we got a fourth. So that means is a half actually maps to -1, and 1/4 maps to -2. So coming over here, when x is a half, y is -1, and when x is 1/4, y is roughly -2. Not roughly, but I'm estimating 1/4 right there, yeah? And so I kind of see a little bit sharper of the sharpness of that curve right there, yeah? And if I think about the features of this graph, all of the x and y features are switching. See, before we had a y-intercept at 0, 1, but now that's an x-intercept at 1, 0. And in the original function, 2 to the x, well, the original function looks something like this. And it had a horizontal asymptote at y equals 0. But if that function's y equals 0, right, if that asymptote's y equals 0, then when you swap x and y, then the inverse function has a different asymptote, x equals 0, which is not horizontal, but vertical. So there's actually going to be a vertical asymptote here, like so. All right? And then I'm going to connect all these points. Ta-da! I'm going to make it nice and smooth there as much as I can. Yeah? And that is our exponential function. Well, the inverse of our exponential function. Yeah? And you'll notice that there's no y-intercept because there's an asymptote on the y-axis. The domain is 0 to infinity. You can see this because there is no negative values graphed here on the x-axis. There's nothing here. The asymptote's at 0, so it starts near it and continues to infinity. The range, however, extends all the way down to negative infinity and all the way up to positive infinity, making that range all real numbers. So, what the heck is this thing, right? It's 2 to the x, but flipped a little bit, right? It's all the features of 2 to the x are flipped. Well, incidentally, this is what we call a logarithm. Yes. And now we're there. So, what is a logarithm? It is simply the inverse of an exponential. In particular, for this function, right, f of x was 2 to the x. But this inverse function, f inverse of x, is called a logarithm of the same base. So we would write this as log base 2 of x. And that is the new function. Yeah, that is what the graph of this is. So, I'm going to take this and say, woo. Okay, and that's it. And the reason I structure the lesson this way is hopefully you kind of remember that shape, right? Because way back in Unit 1, we studied all the parent function graphs. And, if you come over here to Desmos, and there's a button. Where is it? We're looking for log. There it is. Log of x gets you this graph. Yeah? Let me make that nice and bold for you. And so you have this shape, which is what we basically just plotted. Yeah? And it's just like an exponential, like 10 to the x. You can see that these are inverses because there's symmetry about the line y equals x. So the blue curve being an exponential, its inverse is a logarithm. Yeah? And that is how we're going to deal or work with exponentials. So in the previous lesson video, we had this issue where we were trying to find an x-intercept, if you recall, if you watched the first video. Basically, we had set this function equal to 0, but we got to this point where we weren't able to solve the exponential equation. Because in order to solve equations, you have to use what's called inverse operations, right? I mean, think about it, right? If you had x squared equals 49, how do you solve for x? You take the square root, because the inverse of squaring is square rooting. If you had x plus 7 is 10, how do you get rid of plus 7? You do minus 7, because that's the inverse of plus 7. If you had 2x equals 12, this is multiplying by 2, the inverse of multiplication, division, or multiplication by the reciprocal, right? These are all the things that we call canceling, right? You're canceling things out. You're using the inverse operation to get rid of something. So when it comes to exponents, how do you get rid of exponents? You use what's called logarithms. So if you had 2 to the x equals 7, the way you would do this is use a logarithm to isolate x, and you find that x is log base 2 of 7. Now, you might be saying, what? Huh? That's okay. We're going to get there, but what I'm showing you is this is how it works for exponentials. Yeah? Logarithms are a way of getting rid of the base, yeah, to changing the base into some other form so that the thing you're looking for, which is the power, is isolated, is getting taken out of the power, okay? So, we're going to talk about the notation of logarithms and then a few examples, and then some more as we go. So, as I just said, a logarithm is the inverse of exponentiation. So, as just mentioned, it does the reverse of the exponential function. Something to note is that both logarithms and exponentials use the same base. So, if f of x is 2 to the power of x, then f inverse of x is log base 2 of x. Okay? If f of x is 5 to the x, then the inverse function is log base 5 of x. Okay? They use the same base because they're related that way. So you're not going to change the base from the exponential. They're going to use the same number there. In general, as you can see from this notation I've been writing, a logarithm base b is written log base b of x, okay? And just because students ask me this, the parentheses are kind of optional. You are fine to write this as log base b x, like that. They mean the same thing, okay? But the log is a function notation, right? You know how we write f of x, and it doesn't mean f times x, it means put x into f? It's kind of the same situation here. Log is a function notation, right? What you're doing is x is the input into a logarithmic function, depending on what its base is, okay? So that's the style or notation for this. Now, a few other things. There's something called common log, all right? So common log is written in base 10, though it is standard to write common log without the base. So if you see log x with no base, that is the same as saying log base 10 of x, okay? You just don't write the 10, yeah? And you might say, why do you do that? Well, look, remember, you know square roots? You have square root x here, and you have cube root x here, right? And then, okay, fourth root x here. Okay, well, square root, you don't really write an index. You just put the radical sign, right? But technically, you can put a 2 here, right? And that would tell you that that's a square root. But the thing is that we use square roots so often, we just kind of drop the 2 notation. Like, you could put it there, it's fine, but we just don't. It's assumed that the index is 2 for that. Same situation with logarithms. Prior to the invention of electronic calculators, because we did have logarithms before calculators, believe it or not, modern calculators, that is, we really just worked in base 10, and so that was the main log used. You could do like log base 2 of x. You could do this, right? But a lot of times you would use logarithms in base 10 because that's what we had math for, okay? So that's why we have that notation. There's also a special logarithm notation for base e. So that number we talked about, right? E being 2.718. This special number, when used with a logarithm, has a particular way it's written. So it's kind of like saying log base e of x. But the thing is, you don't ever really write it this way. That's not the standard thing. If you were to write that, it wouldn't be wrong. It's just nobody does that, yeah? The way this is stylized is ln of x, all right? That's an L, by the way, not an I. L, so like ln of x. What does this notation mean? The ln stands for, we call natural log, okay? And you say, I don't see the connection there, Mr. Spake. This is weird. I say, give me some time. You're going to get used to it. You say, but the letters are backwards. Okay, here's my justification. In English, we say, look at the red car, right? But in Spanish, you would say, look at the, okay, carro rojo, right? I don't know if I'm mispronouncing that, but I would think that works, right? In Spanish or Latin languages, you put the adjective actually after the noun, right? The car red, yeah, as opposed to the red car. And so it's kind of the same situation here. ln, this comes from a Latin thing, and so it's like log natural. Does that make sense? Yeah, it's like log natural. But in English, we call it natural log, okay? And that's why it's ln, okay? All right. And then the last thing here, this is just a tiny notation thing. You use parentheses to distinguish addition subtraction. So looking at this example, log of x plus 5, this is not the same as log of x plus 5. Okay, those are two different things. Log x plus 5 is like saying log of x and then add 5. So x goes into the log function and then 5 happens after, whereas here x plus 5 is the argument or input into the logarithm. Okay? Okay, just so you know. All right, so what exactly is this? You know, we said, okay, it's the inverse of an exponential. It's written with this interesting, weird notation, log, right? But how does it work? And I say, well, this is the moment in class where I go through these examples, and your goal is to figure out the pattern and how this works, okay? So I'd like you to try the same thing through this video. I'm going to go through this just like I would in class, and I would encourage you to pause the video when we're done to really think about it on your own before I spoil, because Euler, right? Before I spoiler the answer. Okay, so log base 2 of 2. What is this equal to? It's equal to 1. Log base 2 of 4 is equal to 2. Log base 2 of 8 is equal to 3. Again, your goal is, as I go through these, can you predict the answer that I'm going to say? Yeah, you might have an idea just from those first three. I'm going to continue. Log base 3 of 81 is 4. Log base 3 of 1/9 is -2. Log base 3 of 1 is 0. Log of 1,000 is 3. Log of 1/10 is -1. Log of 1 is 0. Log base 5 of 5 is 1. Log base 5 of square root 5 is 1/2. And this last one, natural log of e squared is 2. All right. So I would encourage, if you haven't already figured out, pause the video and time yourself 3 minutes. Take 3 minutes to think about what's going on here. Where is this coming from? Where is Mr. Spake getting these answers? How is this being computed? Yeah? So take a moment and think about it for yourself. Okay. Hopefully that was time for you to pause. I'm going to go ahead and continue and spoil the answer now. So the connection here is all of these answers are the exponents that would go on the logarithm's base to get the argument. The argument is the thing inside the parentheses. So you're saying, what? I say, look, log base 2 of 2 equals 1 because the base 2 to the power of 1 is 2. On the next example, the base 2 to the power 2 is 4. Log base 2 of 8 is 3 because 2 cubed is 8. You see, the base of the logarithm is the same as the base of the exponential. The power is what the logarithm is telling you. The logarithm of that number is the power. The number inside is the result of raising the base to that power. Yeah, and that's true for all of these. 3 to the 4th is 81. 3 to the -2 is 1 over 3 squared, which is 1 over 9. This one's interesting. 3 to the 0, well, anything to the power of 0 is 1. Over here, remember, we were just talking about common log, right? There's no base here. That's implied that it's log base 10. So then the base is 10, which then cubed is 1,000. Again, another common log, 10 to the -1 is 1 over 10. Here, 10 to the 0 is 1. Here, 5 to the 1 is 5. 5 to the half is square root 5. And this last one's fun. because natural log is log base e of e squared. So this is asking the question, the base is e, what power do you put on e to get e squared? Well, the power would be 2, because that's the power, is e squared. Yeah? So all of these results are just the power that you would put on the base to get the thing inside. Yeah? And that's it. That's all logarithms really are. They're an inverted way, because they're literally inverse functions of exponentials. They're an inverted way of expressing exponentials. Okay? So, converting between exponential form and logarithmic form. How do you associate between the two? Well, if you write something in logarithmic form, like this, right? Log base b of a equals x. The equivalent form inverted as an exponential has the base b, the exponent x, which is what it's equal to, is the argument, which is a. And that is the conversion. What this means is you can take any exponential expression and convert it into a logarithm. Yeah? So if you kind of go back to, in that previous video, we were talking about how do you find the x-intercept, right? If you remember this. If you skip that video, it's okay. We had this equation, 2 to the x minus 1 equals 5/3. And the question was, how do you solve for x, right? How do you get x alone? Well, if b to the x equals a becomes log base b of a equals x, then the base b is base 2, a is like the 5/3, and then the exponent is this x minus 1. And then you can isolate x. You can say x equals log base 2 of 5/3 plus 1. And that solves the equation. Because logarithm is a function. What does it do? It does the reverse of exponentiation. And so if you type that into a calculator, you get a number. In fact, I'll show you. Look, you can type this. Log base 2 of 5/3, right? So log base 2 of 5/3, that's a number. It's like 0.7. And then if you add the 1, there it is, right? And so this is your answer. Your answer is 1.7369655, so forth, right? And logarithms help us find those decimal values. Yeah? Okay. And so that's their utility, all right? So we're going to do a little bit of practice converting these forms. This is just some practice for this, so to kind of expose you how it's done. You just do the conversion, all right? Log, where was it? Log base b of a equals x becomes b to the x equals a. So in example 1, right, the b is 2. The argument, which is a, is x, because that's the x right there. And the exponent, the x in this question, is 5. Just note that this x and this x aren't the same thing, right? But these are my a, b, and x for the exponential. So the base is 2, the exponent is 5, and the argument is x. And so see, that actually helps you solve this logarithm, right? Because what is this asking? It's saying, well, for what value of x is log base 2 of x equal to 5? Well, the value of x is 2 to the 5th, right? Which incidentally is 32. So it actually solves the logarithm, right? That's a log equation to solve, and we just found the answer. Because log base 2 of 32 is 5. And the reason that's 5 is because 2 to the 5 is 32. Yeah? So it just goes back and forth, back and forth. Another example. 3 to the 2x is 8. The base is 3. the exponent is this 3x, and the argument or the answer to this is 8. So in logarithmic form, log base b of a equals x. In logarithmic form, this is a base of 3. The input is 8, and the x is the 3x, which is the power. Oh, I'm sorry. Why did I write 2x? The power is 2x, so this would be 2x here. Okay? And that's converting form. So just practicing that, right? I might pause the video, see if you can get these two, all right? But I'll just go ahead and do them. The base here is 10. Base is 10. The exponent is x minus 2, and a is 3. So then it's log base 10 of 3 is the exponent, x minus 2. That's just logarithmic conversion. That's all it is. It's just converting the log. And remember, with base 10, it's not required to write it. So technically, we can just say log 3 of that equals x minus 2. That would, that's what we would typically write. But you can put the 10 if you want, okay? This last one, converting to exponential, natural log is base e. So the base is e, the argument is x plus 1, and the exponent is 5. So as an exponential form, the base is e, the exponent is 5, and the argument is x plus 1. All right? And that's just some practice. It's just going back and forth, from here to here. And it can be a little tough for students at first, but you do this enough times, you'll get it. You'll get the hang of it. It's really not too bad. Yeah? All right. So that's some forms there. Okay. The next part is one of our goals, which is to find the inverse function, which is basically what these questions were doing, but we're going to go all the way and figure out the complete inverse function. Okay? So let's start with number 1 here. How do you find inverses, right? What are your steps? First step is to swap x and y. Second step is to solve for y. Those are the 2 primary steps, right? And you're changing the notation and all that good stuff. So f of x is the y value, and we're going to swap that with x. So f of x is now the x, and that x is now the y. So I swapped it like this, okay? But the goal is to solve for y, or isolate y. So how are we going to do that? Well, the first thing you would do is get the logarithm alone, because in order to use this conversion equation, right, in order to change a logarithm to exponential form, the logarithm has to be alone. All you want is the base and argument. Whatever the exponent is whatever the exponent is. But you need to have your base and argument, and there's no coefficient, there's no power, there's no plus 7 at the end, right? It's just the logarithm alone. So how do I isolate this? Well, I divide by 3. So this gets me as I get x over 3, or rather, I'm going to prefer 1/3 x is log base 2 of y minus 5. Okay, great. So the logarithm is isolated, right? Here's the conversion again, just to keep showing it, Log base b of a is x becomes b to the x equals a. So what's your base, right? The base of the logarithm is 2. B is 2. The argument of the logarithm, a, is y minus 5. And the exponent, what is equal to, is 1/3 x. So this x is the 1/3 x. So just replace all of that for the exponential form. The base b is 2. The exponent, x, is 1/3 x. And this is equal to a, which is y minus 5. Now, this question isn't done, because what's our goal? Our goal is to find the inverse function, which means solve for the inverse y, right? This equation is almost done, but not quite. You want to isolate y by adding 5. So then y is 2 to the 1/3 x, add 5 to the other side, yeah? And since we isolated y, this is now the inverse function. F inverse of x is this, yeah? So the inverse, so that is what we did. We found this is the logarithmic function. Its inverse is that exponential function, okay? And if you don't believe me, go plot it in Desmos, and you will find that. They will have that symmetry over y equals x. Okay, let's do one more for good measure, for good practice. Convert this exponential to a logarithm. Okay, so what are the steps, right? Well, just like you need to isolate the logarithm, if you're working with exponentials, the exponential needs to be isolated, meaning you need base to a power. Then you can convert this to logarithmic form. So if I look at my exponential here, first step is swap x and y. So g of x becomes x, and the 2x becomes a 2y. Now, the exponential, 3 to the 2y, needs to be isolated, so we subtract 8 to the other side, getting us this equation. But now again, we're ready, right? The exponent, it's put in this exponential form where b to the x is a, and that's going to become log base b of a equals x. Well, what's the base? The base of the exponential is 3. So it's log base 3. You see, this 3 is that b, so which is that b, which is that 3 right there. Yeah? The exponent, x, is this 2y, and that's what the logarithm's equal to. So it's going to be an input here, and it's equal to the exponent, which is 2y. And then, right, equals a, this equals x minus 8. So this x minus 8 is like the a, which is that a. And that a is inside the logarithm. So I put x minus 8 here. And we're almost done because the goal is to isolate y. So since it says 2y, we'll divide both sides by 2. Thus, the inverse function, f inverse of x, is log base 3 x minus 8 over 2, or I might prefer to write it as 1/2 log base 3 of x minus 8. Now, if you wrote that over 2, like if you write it like this, that's totally fine. Yeah, that's cool. It's whatever. I just like to write the half as a coefficient as opposed to putting the logarithm over a fraction, but it's the same thing. Yeah, it's equivalent. So there you go. That is finding the inverse for your logarithms and exponentials. It's the exact same process, but they're just reverse of each other, right? In both cases, you have to isolate the expression with the base first. If it's a logarithm, isolate the log. If it's an exponential, isolate the base and exponent, okay? And that usually involves subtracting or multiplying or whatever you need to do. Okay. All right, that's good practice. Let's wrap this up with some graphing practice. So now we kind of understand what a log is. We know how to evaluate it. Again, logarithms just tell you the exponent, yeah? That's just the result of the exponent. So let's go ahead and graph these. Now, I have two examples here, and traditionally in class, I do the first example and then I hand the second example to students. But there's two strategies in doing this. And so what I'm going to do for the video is, in example 1, I'm going to do my preferred strategy. In example 2, I'm going to show you another strategy that a lot of students like. Okay, so if you want to see, you can see both strategies, and whichever one you like, go with that. Okay? All right. So example 1, we're just going to graph this function. You might notice its transformations, right? there is a vertical stretch by 2, right? Vertical stretch by 2, and a shift right 1. Okay, this is semi-useful. And recall, we've talked about the parent function, right? Because the parent function is just this guy right here. This is log base 2 of x, right? So if I pay attention to transformations, this function has a vertical asymptote at 0, and this function's been shifted right 1. So typically you'd have a vertical asymptote at 0, but that's going to move right 1. So I'm actually going to go ahead and put my vertical asymptote from the get-go right there. You don't have to do that as a first step, but I like to. So there's the asymptote, okay? Yeah, great, perfect. So now let's just plug in some numbers. So my strategy for example 1 is to plug in numbers that just make sense. You might say, what? How do I do that? I say, look, you'll get good at this as you do practice, as you do the homework and you just think about these. Think carefully, what x do you want to plug in? Let me show you a bad suggestion. Here's an example. Let's say I pick x as 7, okay? So what that would entail is I would say 2 log base 2 of 7 minus 1. And this would be 2 log base 2 of 6. Okay, well, here's the problem. I don't know what log base 2 of 6 is. You see, because what do logarithms tell you? They're saying, what power do you put on 2 to get 6, right? That's what it's asking. Log base 2 of 6 is what? This is, as an exponential form, this is saying 2 to what power is 6. And the problem is, I don't know that. The answer is log base 2, 6. That's the answer. And so, you know, I don't know this because 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8. Well, 6 is between 4 and 8, so it's got to be 2 point something, right? And indeed, if I go to Desmos, you can see log base 2 of 6, we're going to get rid of the plus 1. You see, it's 2 point something. It's 2.58, right? So it makes sense that it's lying between the exponents 2 and 3, but we wouldn't know that, and that's what logarithms are for. So 7 really isn't the best suggestion because I don't know what log base 2 of 6 is, right? So I'm going to pick something else. So what would smart suggestions be? Well, the argument, you know, the thing inside. When I say argument, I'm talking about the inside of the log. You want the argument to be powers of the base, meaning what are powers of 2? Well, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8. Yeah? So what that means is 1, 2, 4, and 8 are good numbers. These are numbers I would like to get inside that parenthesis. But it says x minus 1. So you have to think, what number would you subtract from 1? Or sorry, what number minus 1 would get you 1, 2, 4, or 8? Well, 2 minus 1 is 1. So if I plug in 2, that's 2 log base 2 of 2 minus 1 is 1. And you see, what is log base 2 of 1? Well, you can evaluate this because this is just asking, what exponent do you put on 2 to get 1? That exponent is 0, right? So then this is 2 times 0, which is 0. Okay. Then the next point is 2. Okay, so what would I plug in for x? What minus 1 is 2? 3. So if I plug in 3, then I get 2 log base 2 of 3 minus 1 is 2. Okay, well, what power do you put on 2? 2 to what power is 2? The answer is 1. So that's 2 times 1, which is 2. And we're just continuing this fashion. What minus 1 is 4? 5 minus 1 is 4. Then 2 log base 2 of 4, right? What 2 to what power is 4? 2. 2 squared is 4. So then this logarithm comes out to 2, and 2 times 2 is 4. One more. Let's get the 8. 9 minus 1 is 8. So then that's 2 log base 2 of 8. So I'm gonna plug in 9, right? Log base 2 of 8 is 3, because 2 cubed is 8, and 2 times 3 is 6. And thus, I have my 4 points. Those are pretty good points that I'm going to go ahead and plot on the curve. 2, 0, 3, 2, 5, 4, and 9, 6. And then you could plug in some fractions, but we have that asymptote there. So we know it's going to flatline at the asymptote and then bend and go outward, upward through all those points like so. And that's my log function, like so. Done. Yeah. Now, this is my preferred strategy because I'm very comfortable now with logarithms, having done them for a while. And I understand that the goal is for the inside to be powers of the base. So if the base is 2, you want 2, 4, 8, 16, right? If the base was 3, you would want 1, 3, 9, 27. If the base was 10, you would want 1, 10, 100, right? So if you understand that, this is a good strategy because you just figure out what you want to use for x. Looking at this graph, we will notice a few things. The x-intercept is at 2, 0. The y-intercept is nowhere to be found. It does not intersect the y-axis. The asymptote's at x equals 1. The domain goes from the asymptote 1 to infinity, and the range is all real numbers. And for logarithms, the range will always be all real numbers. Okay, that is strategy 1. It is possible you don't like that strategy, and that is cool, all right? I like this strategy, but you don't have to do it that way. I'm going to do example 2 now and demonstrate a different strategy that it's a little bit more work to get to, but then once you have it, that it's really, really easy to plug numbers in. You see, the difference being, if you understand what numbers to plug in, this is very easy. But if you're saying, I don't know why he's using 9 or 5 or 3, then you might prefer this strategy. And so what we're going to do is, you say, well, you may struggle with logarithms, but you know exponentials. You've done them in Algebra 1. Well, we just went through how to find an inverse function, right? You swap x and y, and you solve for y. So in this equation, y equals log base 3 of x plus 4 minus 2. What I'm going to do is I'm going to switch y to x, and I'm going to switch x to y. And I'm just going to find the inverse function real quick. So I would add the 2 to x, so I'd get this. This would isolate my logarithm, so I would have log base 3 of y plus 4. Now remember, the conversion, one more time, log base b of a equals x becomes b to the x equals a. So what's the base? The base of the logarithm is 3. The exponent that's on the base is this x, which is the other side, which is x plus 2. It's the other side of the equation. And then this is equal to y plus 4. To isolate y, subtract the 4, and I have y equals 3 to the x plus 2 minus 4. Well, this is an exponential function, f inverse of x. This is the inverse of the function we were given. But what's nice about this is it's so easy to plug in numbers. Look, make a table for this. Plug in -2, -1, 0, 1. Yeah? Watch what happens. -2 plus 2, so you say 3 to the -2 plus 2 minus 4. Well, that's 3 to the 0, which is 1, and 1 minus 4 is -3. Repeat, plug in -1, right? -1 plus 2 is 1. 3 to the 1 minus 4 is 1. 3 to the 0 plus 2 is 3 squared, which is 9. Minus 4 is 5. And then one more, 3 to the 1 plus 2. Well, that's cubed. So that's 3 cubed is 27. Minus 4 is 23. Well, that's a little too big, right? So I don't really need that last one because it's not going to fit on my graph. But those points were very quick and easy to find. The hard part was just doing the inverse function, right? But now that I have the inverse function, it's a more familiar exponential, and you can just plug in easy numbers, like single-digit numbers, and you're going to get them, right? And that will be nice, and it'll always work out. So what do you do with this? Well, you don't plot this table because this is the inverse function. You want to plot the original function. But all the original function is the flip of the inverse because that's what the inverse is. It's the flip of the original. So you take these points and flip them. -2, -3 is actually -3, -2 on the original graph. And then the other points, 1, -1, 5 and 0, technically 23 and 1, though that's not going to fit on my graph here. Yeah. I actually didn't want to erase that. So there we go. So let's plot it. -3, -2 is right here. 1, -1 is right here. 5, 0 is right here. Yeah. I'm sorry. That one wasn't 1, -1. It was -1, 1, I believe. Yeah. Yes. Yeah. I was thinking that doesn't look right. I've flipped it wrong. So then -1, 1 is -1, 1. That's right here. Okay, that's better. Wait, what? 0, 5. Guys, did I mess up? You plug in 0, you get 5. Hold up. Let me make that. I'm so sorry. This is why Mr. Spake doesn't like this method as much. I think I either plugged in the points wrong or something. Let me just recompute this. 3 to 0 is 1. 1 minus 4 is -3. Right? 0 plus 2. No, so -2 is 0, 1 minus... Okay, that's true. So then the point is -3, 2. Okay, true. You plug in -1, you get 3 minus 1 is -1? Is that right? -1 plus 1 is 3. Okay, that's where I went wrong. So they're both negative. Okay, my apologies. Okay. Do your math right, Mr. Spank. Do your math right. There we go. Oh, there we go. That's nice. Okay. Yeah, beautiful. So I've got all those values, right? And if you wanted some fraction values, right, you could have tried 3 to the -3 plus 2, which would be 3 to the -1, which is 1/3 minus 4. So you could get some fraction values this way too. The fractions are a little harder to do with the log form, but they're easier with the exponential form. But that's 3 points. And what other features do I know? Well, the transformations shift left 4, because it's x plus 4, and down 2. So then the original asymptote for logs are at 0 right here, but you moved it left 4, so the vertical asymptote is now there. And so then now I can connect these points, flatlined at the asymptote, and then connect through those points. Like so. Ta-da! And thus I have my beautiful, beautiful logarithmic function. Yeah? As far as x-intercept goes, that's 5, 0. The y-intercept, well, that happens right there, which happens when x is 0. So the thing about the y-intercept is it's log base 3 of 0 plus 4 minus 2. Well, 0 plus 4 is 4, so that's log base 3 of 4 minus 2. Thing is, 4 is not a power of 3, right? Because powers of 3 are 3, 9, 27. So we don't know what log base 3 of 4 is without a calculator. But if you want, you can skip this if you'd like, but if you want to be technically correct, it's 0, comma, log base 3 of 4 minus 2. That's technically the y-intercept. You might say, well, how are you supposed to know what that is? Well, that's why we got calculators, right? Log base 3 of 4 minus 2. That would be the y-intercept. And if you don't believe me, let's look. I'm going to graph the logarithmic function, log base 3 of x plus 4 minus 2. There's the y, right? See, this is the graph we got. See the black curve? Compare this to our beautiful graph there. Basically the same thing, right? So yeah, and that y-intercept, as evidenced on the point right there, matches the decimal that we wrote up there, okay? So when it comes to this stuff, we are eventually going to introduce calculators, and the calculators will tell you what that number is. Your asymptote, as we said, is at -4. Your domain goes from -4 to infinity because there is no graph prior to the asymptote, so it goes from -4 and on, and the range is all real numbers because it goes up and down forever. And there we go. That's the logarithmic function. So I hope this, I know this video's taken a while. I know it's a very long video, but it's very, very new. Logarithms are very new, and it's going to take a good amount of practice to get used to them. But once you got the hang of it, they're not too bad anymore. Yeah, sometimes they're initially a little, I'm not going to say scary, but they can be a little confusing at first because the notation is a little different. But practice makes perfect, right? We'll keep practicing. You'll come to really, really like these. They're actually super useful. We love them. And that is that. So I hope these two strategies demonstrate, right? Whichever you want to do, if you want to plug in points, do that. If you prefer to find the inverse function and plug points into that, then flip the table. That's a great way too. Okay, both are valid. And this second method is very good algebra practice, right? So there's some merit in doing it that way as well, just as additional practice in working with logarithms. Okay. And so, yeah. Should I leave it there? No, let's finish this out. There's one more thing. The thing is this is only going to take 5 minutes, so I don't want to make this a part 3 because it doesn't take any time at all. There's one last piece of the lesson right down here, and it takes a break from logarithms, and it goes back to exponentials. So it says rewriting exponential functions. It says we can play around with exponential functions depending on the information you're given. What we're going to do here is do a sort of algebraic maneuver in rewriting exponential expressions into simpler terms, okay? What is the point of this? Well, it's an algebraic technique that often proves itself useful in certain situations, okay? So here's what we do. Here's the goal. Rewrite the exponential function. F of x is that right there, 27 times 1/9 to the x. Rewrite this in the form a times b to the x, such that the coefficient a is 1 and b is a positive whole number. So you don't want a fraction there, because right now a is 27 and b is 1/9. The goal is to rewrite it in such a way that this is 1 and this is a whole number. So how do I do this? Well, the thing is, 27 and 1/9 have something a little bit in common. And you say, what do they have in common? I say, look, think about 9, think about 27. Think about exponents, right? What's special about 27? Well, 27 is 3 cubed. Okay, great. What's special about 9? Well, 9 is 3 squared. And in fact, 1/9, right? If you recall, 3 to the negative 1 is 1 over 3. And that means that 3 to the negative 2 is 1 over 3 squared. But 3 squared is 9. So there's 2 bits of information here. 27 is 3 cubed. And 3 to the negative 2 is 1/9. So here's what we're going to do. We're going to take this function, 27 times 1/9 to the x, and you're going to rewrite 27 as 3 cubed, and you're going to rewrite 1/9 as 3 to the negative 2, which is then raised to the power of x, because there's that power of x right there. Now, because we're familiar with properties of exponents, there's something you can do here. You can combine this into a simpler expression. First rule is right here. You're raising a power to a power. Well, 3 to the negative 2 to the x is like equivalent to 3 to the negative 2x. Because when you raise a power to a power, you multiply them. Yeah? So I'm gonna circle this. We have this component right here. Okay? So let's go back to red. Then what I have is 3 cubed times 3 to the negative 2x. Well, if you're multiplying 2 bases that are the same, what are you allowed to do? I say, look, if you had x to the 3 times x to the 5, you'd say, oh, Mr. Speck, I know this. X to the 3 times x to the 5 is x to the 8th. And I say, congratulations, student. How did you do this? You say, well, because 5 plus 3 is 8. The rule when multiplying the same base is to add the exponents. So because both of these have a base of 3, you can say that this is 3 to the power of negative 2x, then added with 3. And notice what we've done here is we've rewritten this expression in terms of a single base, right? A whole number integer base, 3 to the negative 2x plus 3. Yeah? You might say, again, Mr. Spake, what is the point of this? I say it's to show you that it's something you can do. Yeah? This is an algebraic technique of manipulating an equation and using bases to essentially rearrange and rewrite. Yeah? And that's it. That's all it is. All right? So, there you go. Now, there is a follow-up question. Is this a growth or decay function? This is a pretty good question. So if you look at the original function, 27 times 1/9 to the x, right? Well, how do you know if something's growth or decay? Well, in the first part of the video, if the base is more than 1, it's growth. But if the base is less than 1 and positive, then it's decay. The base in this case is 1/9. B is 1/9. That means 1/9 is less than 1. Therefore, this is a decay function. Yeah? So looking at this, you know that this function is a decay function because of the 1/9. But then, how could you know that from the rewritten expression? Right? You see this 3 to the negative 2x plus 3? How could you look at 3 to the negative 2x plus 3 and know that that's decay? Well, if you think about transformations, 3 to the x is a typical exponential growth function. But 3 to the negative x does a horizontal reflection, meaning it flips and becomes a decay function. So, because this says negative 2x here, the coefficient on x is negative. That means there's been a horizontal reflection applied. So instead of being growth, it's been reflected and it becomes decayed. So I know topically, I might need to arrange this next year because I know we just had such a wonderful video on logarithms and then this weird thing at the end. But I wanted to fit it somewhere, so I thought I would stick it here. Yeah. So anyway, that is the video. I know it was a long one, but thank you so much for watching. I hope that you find some utility, some guidance in these videos. I know they could be a long watch, but I hope it helped. And if you have any questions, as always, just come see me at Raider Time, ask me questions. Love to help you because I really, really love logarithms. And I know that, the notation is very brand new. Happy to talk about them and give you some more practice. So thanks for watching. Take care. Have a good night or morning or whenever you're watching this. And I'll see you in the next one.